Hey everyone, and welcome. We're about to dive into something that's honestly one of the most important parts of building a great AI model. We're talking about hyperparameter tuning. This is the real secret sauce, you know? It's what separates a good model from a truly fantastic one.
So let's think about it like this. Imagine you've got this incredible race car, right? The engine is a beast, but raw power just isn't enough to win. If your suspension isn't dialed in, or you've got the wrong tires for the weather, you're just not going to make it to the podium. That's exactly what hyperparameters are. They're all those little tuning knobs. We're the mechanics, and it's our job to tweak those settings to squeeze every last bit of performance out of our AI model.
All right, so how do we actually do this tune-up? Let's pop the hood and take a look at the tools we have in our garage. But first things first, we need to be crystal clear on what exactly we're trying to tune.
Okay, so what is a hyperparameter? Well, it's basically a configuration setting that's external to the model. You, the data scientist, have to set its value before you even start training. The model itself can't figure these out from the data. Good examples are things like the K and a K nearest neighbors model, or, like we'll be looking at, the number of trees, what we call N estimators, in a random forest. These are the dials we have to get just right to win the race.
So our first tool in the toolbox. This one's for the perfectionist. You know, the mechanic who leaves no stone unturned, who has to check every single bolt. Let's talk about the meticulous grid search.
And really, the name kind of gives it away, doesn't it? Grid search is exhaustive. It's a complete brute force method. What it does is it lays out this, grid of every possible combination of hyperparameters you tell it to check, and then it just goes through them, one by one. It trains a model, evaluates it, and moves to the next. It is incredibly thorough.
The process itself is actually pretty straightforward. First, you just define that grid of all the parameter values you want to test. Then, the machine chugs away, training a model for every single one of those combinations. Now, here's the key part. It uses cross-validation to evaluate each model to make sure the score is reliable. And at the very end, it just spits out the winner, the combination with the highest score. Simple, right? But also really powerful.
So you might be wondering, what does one of these grids actually look like in practice? Well, here's a perfect example. For our random forest model, we're telling it, hey, for the number of trees, or N_estimators, try 50 and 100. For max depth, try 3, 5, or no limit at all. And for min-sample split, let's test out 2 and 5. That's our grid.
Okay, but here's where it gets really interesting and kind of expensive. Let's do the math. We've got 2 options for estimators, times 3 for depth, times 2 for splits. That gives us 12 unique combinations. But wait, there's more. Remember, we're using 5-fold cross-validation for each one. So that's 12 combinations times 5 folds, which means we are training and evaluating 60 separate models. 60! That's the price you pay for being so thorough.
So, what if you don't have the time for that? Or maybe the computing power to train 60 or 600 or 6,000 models? Well, that's where our second tool comes in. Let's talk about the much more efficient, kinda savvy alternative, random search.
And this really gets to the heart of the difference between the two. With grid search, you're doing this exhaustive search, but only on the specific values you put in the grid. Random search, it's a bit smarter. Instead of a fixed grid, it samples random points from a much wider distribution of values. The big idea here is that you don't need to test everything to find a great model. A few smart, random guesses can get you there way, way faster.
So yeah, instead of that brute force, try everything approach, randomized search just takes a fixed number of samples, and it picks them from probability distributions that you get to define. This is an absolute game changer when you're dealing with a huge search space, or when some of your parameters are continuous numbers. And this is what that looks like in the code. See, instead of a fixed list like 5100, you give it a range to play in, like randint 10-200. This is just telling the search, hey, for N estimators, pick any random whole number you want between 10 and 200. Suddenly, we're exploring a huge range of possibilities, not just 2 specific points.
And here's the magic parameter, N-iter. That just stands for the number of iterations. We've set it to 15. That means we're only going to test 15 random combinations of settings. Just 15. Now think back to grid search. It had to train 60 models. We're getting to explore a much bigger space of possibilities, but we're doing it in a quarter of the time. That is a massive win.
Okay, so let's say we've run our search, we've found the best settings, and our model is just singing. We're getting amazing performance. But hold on. Before we pop the champagne, there is one golden rule, and you absolutely positively cannot forget this.
So you run your search, and it comes back with an awesome cross-validation score. Let's say 0.978, almost 98% accuracy. That's fantastic. So that's our final score, right? We can just report that number and call it a day?
No, absolutely not. And if you take away only one thing from this whole explainer, let it be this. The golden rule is you never, ever, ever tune on your test data. Just think of your test set as the final exam. It's in a sealed envelope and you're not allowed to look at it. If you use that data to tune your model, it's like you're letting the student, your model, see the exam questions beforehand. We call this data leakage. Of course it's going to get a great score, but that score is fake. It's inflated. It's what we call optimistic bias. And the second you show that model some brand new real-world data it's never seen before, it's going to fall flat on its face. It hasn't actually learned, it's just memorized the answers.
Okay, so with that incredibly important rule in mind, let's wrap this up. Let's figure out when you should reach for grid search, our meticulous mechanic, and when you should go with a faster, more savvy random search.
Here is your go-to guide, your cheat sheet. Basically, you want to use Grid Search CV when your search space is pretty small and manageable. You know, if you have fewer than 100 combinations, go for it. The big benefit is that it guarantees you will find the best possible combination within that specific grid you defined. But for pretty much everything else, if you have a large search space or continuous values, Randomized Search CV is going to be your best friend. It will almost always find a great, if not the best model in way less time.
And just to be super clear, here is the correct final workflow. Step 1, you do all your tuning, grid search, random search, whatever, using cross-validation on your training data only. Step 2, you take the winning set of hyperparameters from that process. Step 3, you train a new single final model using those best parameters on your entire training dataset. And only then, once that final model is built and ready, do you break the seal on the test set and see how it really performs on data it has never ever seen before.
So there you have it. We've tuned our AI race car to perfection. We followed the rules, we aced the final exam, and we got the highest possible score. But that leads to a really interesting question, doesn't it? In the real world, is the model with the highest accuracy score always the best model for the job? Something to think about. Thanks for joining.